Let's say we have a plank of wood which we would like to use to cross a canal. It has a rectangular cross-section, so we could either use it like we have done here, or we could rotate it onto its side like this. Intuitively, we can tell that the plank will be stiffer if the load is applied to the shorter side of the cross-section. Some cross-sections are much more efficient at resisting bending than others. The further the material is spread from the bending axis, the stiffer the cross-section tends to be. The cross-section on the right has more material located far from the bending axis and so is better at resisting bending, even though both cross-sections have the same area. This concept of resistance to bending can be quantified by calculating the area moment of inertia, which is also sometimes called the second moment of area. The area moment of inertia reflects how the area of a cross-section is distributed relative to a particular axis, and so is a measure of how much resistance the cross-section has to bend. The I-beam locates the majority of the material as far as possible from the bending axis, and so is a very efficient cross-section. This is why it is so commonly used in construction. The major function of the beam is to resist the moment generated by applied load or to resist the deflection which generates again high moment on the beam. We want beams to have smaller amount deflections and carry more loads. That's the whole idea. So, the beams are designed to resist bending stresses with a large value of flexural rigidity I. Young modulus or modulus of elasticity. Young's modulus is a material property that tells us how strongly a material resists deformation or deflection, and is defined as the ratio of tensile stress to tensile strain. I, the second moment of area or the moment of inertia of a shape. It is a measure of the efficiency of a cross-sectional shape to resist bending caused by loading. Units are mm to the power of 4. For a given material, E is constant, and the value of the moment of inertia, I, depends upon the sectional dimension of the beam. Moment inertia of rectangular cross-section. I equals B, d cube, over 12. From the above formula, beams with higher moment of inertia will have lesser deflection and carry more loads. Also, I increase linearly with width but increases by 3 orders of magnitude with depth. Hence, obviously, it is more beneficial to have more depth than width. According to the flexural stress formula. So, what does this formula tell us? Bending stress increases linearly as the bending moment and the distance from the neutral axis increase, and it decreases as the area moment of inertia increases. The maximum stress occurs at the fibers furthest from the neutral axis. Thank you very much for watching. Please do make sure you subscribe to the channel by clicking the red button below the video. That way you aren't going to miss out on any of the videos that I upload. Also, I would very much appreciate it if you gave the video a thumbs up. Thank you very much. I hope you have enjoyed that and it has gotten some way to helping you. I sincerely hope you understand why the breadth of the beam is shorter than the depth. Thank you so much. Have a great day.